Alrighty, if we look at, we're in notes number 3, and we want to go to the very last example. The last example is one that we got to yesterday, but we did not finish it. What makes example number 5 challenging is that, as people pointed out yesterday, we have some of each of those 3 chemicals. And that is in contrast to what we see, and I apologize for the board work, but you can see in this problem, when we first started, we had zeros. And those zeros they have no choice but to go up. So we know that this side on the right is going to gain. It's going to go up by x, up by x. We say, because this is the gaining side on the right, they did a good job with this, in my opinion. We say that the system will go from what it is initially, it is going to shift to the right, meaning the right is going to gain. If you want to think of the aquarium demo, it's going to gain water. So it is shifting to the right, from the left to the right. All right? So if we look at example number 5, the question that we have to know, or we have to ask ourselves, does the system shift to the right to achieve equilibrium, where it goes up on the right side and down on the left side? Or does it go to the left and we lose on the right? So once again, going to the visual here, I've got some water in both aquariums. So what should I do? Hey, it's going to shift to the right. So I pour water over there. Okay, now we're at equilibrium. Or, no, you have way too much on the right. That's going to be equilibrium. Does it shift to the left? So here's what we're going to do. And it's a simple idea, but it's not something we've talked about. The variable is Q. Q. And the mathematical relationship for Q is this. I'm going to write the generic Q equation. HI squared over H2 times I2. And that looks a lot like products over reactants, and the coefficients matter. Yes, it does. Here's what I want you to think about. This K number of 54.3 for this equation, that K is attached to the equilibrium line. And it makes sense to me because the K is known as the equilibrium constant. So it describes equilibrium, the eventual end. Q, I always remember it as this, whether you agree or not. Q is all about I, the initial. And the way I remember it is, if you're smart, I guess you're supposed to have a high IQ. I don't know if that's true or not, but I remember IQ. All right, the Q is attached to the initial molarities. So what we'll do is we're just going to substitute in these molarities into this equation and calculate, well, what is Q, the initial condition ratio here. So we go 0.0224 squared over 0.00623 times 0.00414. When I did that, I got an answer of 19.5. So I have my K value, and I now have my Q value. And we're going to compare those two numbers. Now, anytime you compare two numbers, and I want you to write it out here. I want to save space for my rice chart, but I can do a K versus Q where I say, okay, fine, K is greater than Q. Well, maybe K is less than Q, or maybe K is equal to Q. 3 options exist. In this problem, I know my Q value is 19.5. I know my K value here is 54.3. So I can say without a doubt, if I'm comparing those two numbers, well, I can tell you K is greater than Q. And so I'm just going to mark this. K is greater than Q. Well, a student of mine a number of years ago who sat right where Kyle sits, believe it or not, name is Rob Shepard. He's in the Bracken Hall of Fame because he came in after I tried to teach this and he said, hey, I have something I think you're going to like that's going to make this K versus Q when you compare the numbers. It's going to make it really easy. And I said, oh, do share, absolutely. And he said, okay, you have to write the letters K and Q in alphabetical order. But you probably don't have to worry about that, Bracken, because everybody knows K comes before Q in alphabetical order. So I said, all right. And he said, if you write greater than, less than, or equals greater than, less than, here's the thing. If you've written it in alphabetical order, the greater than or the less than sign, think of it as an arrow. It is going to point you in the direction of the shift that will occur. And I said, so hold on. You want me to think of this as like an arrow? Yes. So if K is greater than Q, the system is going to shift to the right. If K happened to be less than Q, it's pointing in the left direction. And if you're like, all right, but what if they're equal? There's no shift because you are already at equilibrium. So it'll point you in the direction. The only thing I would add to your notes here would be if K is equal to Q, no shift occurs. So since K is 54.3 and Q is 19.5, oh ho ho, it is easy. Down by, and you're going up by 2x because of that coefficient of a 2. Therefore, at equilibrium, we have 0.00623 minus x, 0.00414 minus x, and 0.0224 plus 2x. And now, it's just like what we did yesterday. It's just like what we did yesterday, where we say, well, I can tell you right now, this is the line of interest, and I know my K value. I'm going to plug it in. I'm going to solve for x. So away we go. Here's the answer that I got. I know that K is equal to 54.3, and that is going to be equal to 0.0224 plus 2x squared over 0.00623 minus x times 0.00414 minus x. When I put that into my calculator, I get x is equal to 0.00157. There we are. Once I know my x value, like every problem, hey, what are those molarities at equilibrium? I'm going to substitute. And here we go. I'll give you those answers so that way you've got them. H2 is going to be equal to 0.00623 minus 0.00157, and that is equal to 0.00466 molar. I2. Hey, it started at 0.00414, and it goes down by x, 0.00157. Answer there is going to be 0.00257 molar. HI. That started at 0.0224, and it's going to go up by 2 times x, 0.00157. And final answer there, 0.0255 molar. Not difficult at all. Not difficult at all. What we're going to work on for the rest of the class is getting to know our graphing calculator. Those who are watching at home, I'll work with you when you come back to school, or you'll work with a friend, but we'll figure that out. Okay?